Welcome back to A Quiet Place to Rest, where we gather each night to wonder about the universe and the strange, beautiful mysteries it hides. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Tonight, we are going to travel somewhere that feels far away, even though it sits directly beneath your feet. Picture yourself drifting upward, gently away from the room you are in, up past the ceiling, up past the rooftops, the trees, the slow drifting clouds, higher still into the cold blue of the upper sky, until the air thins into nothing and the curve of the earth begins to appear below you. From here, our planet looks calm. A soft blue sphere streaked with white, a world that seems peaceful, finished, complete. Now, turn around and look back down. Imagine, just for a moment, that the earth becomes transparent beneath you. The blue oceans fade, the green continents become glass, the brown crust softens into something you can see through. And as you look deeper, layer by layer, you begin to understand that the world you live on is not really what you thought it was. The surface, the part we know so well, is the thinnest sliver, a delicate shell of cool rock, only a few dozen miles thick in most places. Beneath it lies the mantle, a vast region of hot, slow-flowing rock that moves like warm honey over millions of years. It carries the continents on its back. It builds mountains. It feeds volcanoes. And yet, even the mantle is not the strangest place inside our planet. Below the mantle, almost 2,000 miles down, the world changes completely. The rock gives way to metal. An enormous ocean of liquid iron and nickel swirls in the darkness, hotter than the surface of many stars. It is a sea no light has ever touched, a sea no creature has ever seen. And inside that sea, at the very center of everything, there is something even stranger. A solid ball, a sphere of iron, roughly the size of our moon, spinning quietly in the heart of the world. This is the inner core. And for as much as we have learned about it, it remains one of the deepest mysteries in all of science. Think about that for a moment as you settle in. There is a moon-sized ball of crystal iron at the center of our planet. It glows with heat. It spins. It may spin at a slightly different speed than the rest of the Earth, and it sits suspended in a churning ocean of molten metal, held in place by gravity and pressure so immense that the laws of matter begin to bend. We have never seen it. We will never see it. No probe will ever reach it. No camera will ever photograph it. The pressure down there would crush any machine we could ever build, instantly, into a smear. The temperature rivals the surface of the sun, and yet, somehow, we know it is there. We have pieced together its existence through clever listening, through earthquakes, through the slow detective work of generations of scientists. What we have learned is astonishing. What we have not learned is even more so. We do not know exactly how the inner core formed. We do not know exactly what it is made of. Beyond iron and a sprinkle of lighter elements, we cannot quite identify. We do not know why it sometimes seems to slow down and speed up. We do not know whether there is another, even deeper ball hidden inside the inner core itself. And we do not know how long it has been there, or how much longer it will last. For tonight, that is the place we are going to rest our minds. Not on the surface of distant planets, not in the cold reaches of empty space, but here, beneath us, closer than the moon, closer than the nearest city, just a few thousand miles straight down, through layers of rock and fire and metal, where a quiet iron heart turns slowly in the dark. It is older than every mountain, older than every ocean, older than every living thing that has ever walked the earth, and it has been spinning there in silence the entire time. As you breathe, as you settle, as the day softens behind you, let your thoughts drift downward instead of outward. There is a hidden world beneath your feet, and it has been waiting patiently for someone to wonder about it. Before there were satellites, before there were deep mines, before there was any way to peek inside our planet, people simply guessed. The ground felt, the stones felt heavy. And so for most of human history, the inside of the earth was a story, told in different ways by different cultures, but always told without proof. The truth, when it finally arrived, came not from digging but from listening. And what we heard surprised us. The first real clue came in 1906. A British scientist named Richard Dixon Oldham was studying the wiggles drawn by seismographs after distant earthquakes. A seismograph is a machine that records the shaking of the ground, the way a pen on paper might record a heartbeat. Oldham noticed something strange. The shaking arrived at faraway stations later than it should have, as if some hidden thing inside the earth were slowing the waves down or bending them off course. He suggested, gently, that our planet might have a core, not a uniform ball of rock all the way through, but a separate region at the center, made of something different. Then, in 1936, a Danish seismologist named Inge Lehmann took the idea one step further. She studied the patterns of waves from a large earthquake in New Zealand. She saw faint echoes arriving in places where no echoes should have arrived. The simplest explanation, she said, was that the core itself had a core, a smaller solid ball nested inside a larger liquid one. Her paper was short. Its title was just the symbol P', but the idea inside it changed how we picture our own planet. So what is this hidden thing, in the simplest terms? Imagine the Earth as an enormous onion made of layers wrapped around layers. On the outside, the thin skin we live on, called the crust. Under the crust, a thick layer of warm, slow-moving rock called the mantle. Below the mantle, a deep ocean of liquid metal. And at the very center, a solid ball of iron spinning quietly in the dark. That solid ball is what we now call the inner core. It is about 1,500 miles across. That is roughly the width of the continental United States, from one coast to the other, rolled into a sphere. It sits about 3,200 miles beneath your feet, which is farther than most airline flights you will ever take, only pointed straight down instead of across. Around it sloshes the outer core, a churning ocean of molten iron and nickel, about 1,400 miles thick. If you could somehow stand at the boundary between the two, you would see a solid metal floor below you and a glowing liquid sky above. The temperatures at that boundary are thought to reach close to 9,000 degrees Fahrenheit, which is roughly the surface temperature of the sun. And yet, despite that heat, the inner core stays solid. The pressure squeezing down on it is so enormous that the iron atoms cannot melt. They are pressed too tightly together to flow. The age of this iron heart is one of the open questions we will sit with later. The Earth itself is about 4.5 billion years old. The inner core, though, may be much younger. Some studies suggest it began to freeze out of the liquid metal only about 1 billion years ago. Others suggest it could be older, perhaps 2 or 3 billion years. The honest answer is that We do not yet know. We are still measuring, still arguing, still listening to the faint signals reaching us from below. The composition is also only partly known. Most researchers agree the inner core is mostly iron, with a smaller amount of nickel mixed in, but the density we measure does not quite match pure iron. Something lighter must also be down there. Sulfur, oxygen, silicon, carbon, hydrogen, all have been proposed. Which one, or which combination, is still being worked out. These are the bones of the story. A ball of iron, the size of a small planet, hidden inside our own planet, surrounded by a sea of liquid metal, hotter than lava and squeezed by pressures we cannot easily imagine. It has been there, in some form, for most of Earth's history. It is there right now, beneath your bed, beneath the floor, beneath the deepest cave anyone has ever found. And we discovered it, not by reaching it, but by listening to the way the planet sings after it shakes. In the sections ahead, we will follow that song down, layer by layer, into the parts of the story where the certainty fades and the open questions begin. No one has ever seen the inner core. No camera has ever traveled there. No drill has come close, and no drill ever will. The deepest hole humans have ever dug reaches barely 12 kilometers down, and the core begins almost 3,000 kilometers below that. The pressure crushes any tool we could send. The heat melts any metal we could build with. So the question becomes simple and strange at once. How did we ever come to know there was anything down there at all? The answer is that we listen. We listen to the planet itself when it shakes. Every earthquake, no matter how small, sends out waves of energy in every direction. These waves travel through the rock, through the mantle, through the molten outer core, and through the solid heart at the center. They behave a little like ripples in a pond, but in 3 dimensions, moving through layers of different stuffs at different speeds. And when they finally arrive at sensors on the far side of the planet, they carry quiet messages about everything they pass through. Seismologists, the scientists who study these waves, have learned to read those messages. They notice when a wave arrives a little earlier than expected or a little later. They notice when a wave seems to vanish entirely, only to reappear in a place it should not be. They notice when a wave bends, or splits, or slows down, or speeds up. Each of these tiny changes is a clue about the material the wave passed through. Soft material bends waves one way, hard material bends them another. Liquid blocks certain kinds of waves completely. That last clue is the one that opened the door. There are 2 main types of seismic waves. Pressure waves push and pull through anything, solid or liquid. Shear waves only move through solids because they need something rigid to push sideways against. In the early 20th century, a researcher named Richard Dixon Oldham noticed something unsettling. Shear waves seemed to disappear when they tried to cross through the center of the Earth. Pressure waves got through, but shear waves did not. The simplest explanation was that somewhere deep inside, there was a vast region that was not solid at all. It was liquid. That single insight, drawn from the way the ground trembles, was the first true glimpse of the core. The next great clue came from a Danish scientist named Inge Lehmann, who in 1936 spotted something even stranger. Some pressure waves were arriving in places they should not have been able to reach. They had bounced off something deep inside the supposedly liquid center, something hard, something solid. From this, She suggested that within the liquid core, there must be an inner ball, a smaller sphere made of solid material. Her idea has held up ever since, though many of the details remain quietly contested even today. It is a humbling thought. We came to know the inner core not by seeing it, but by listening to the planet ring like a bell each time it shifts. Every earthquake is, in a strange way, a flashlight shone through the dark interior of our world. The light is faint, the shadows are deep, and we are still learning to read what comes back. Modern seismologists have far better tools than Oldham or laymen ever had. Networks of sensors now blanket the surface of the planet, recording the smallest vibrations with extraordinary care. Computers compare the arrival times of thousands of waves from thousands of quakes, building rough maps of what lies beneath. These maps are blurry, they are uncertain. Different research teams sometimes draw different pictures from the same data. One group may see a smooth boundary between layers, another may see a rough one. One may suggest the inner core spins faster than the surface. Another may find no clear spin at all. The disagreements are not failures, they are the honest edges of what we can know from so far away. There is something gentle about all of this. The inner core has been there for billions of years, quiet and unseen, and we have only begun to glimpse it by accident, through the trembling of distant ground. We do not have a photograph. We do not have a sample. We have only the faint signatures left by waves that traveled through it and came out changed. From those signatures, we have built a picture that is partly knowledge, partly guess, partly imagination. Whether that picture is close to the truth or only the beginning of a far stranger story is one of the quiet, open questions waiting beneath our feet tonight, while the planet hums on and the deep iron heart keeps its silence. Somewhere beneath your feet, deeper than any mine has ever reached, there is a place where the world stops being rock and becomes metal. Picture a smooth, hidden shell about 2,900 kilometers down. Above it, the mantle moves like thick, hot stone, slow as honey on a cold morning. Below it, an ocean of molten iron churns in the dark. The line between them is called the core mantle boundary, and it is one of the strangest places in the planet. This boundary is not a clean, flat surface. The best models suggest it has gentle hills and valleys, perhaps a few kilometers tall. Some regions seem stranger still. Deep beneath parts of Africa and the Pacific, scientists have mapped huge, soft blobs of rock that sit on top of the core like puddles. They call them ultra-low velocity zones because seismic waves slow down sharply when they pass through them. Nobody is entirely sure what these patches are made of. One idea is that they hold dense, partly melted rock left over from the planet's youth. Another is that they are pockets where the core itself is leaking iron up into the mantle very slowly over billions of years. What lies below that boundary is mostly iron, about 85% by current estimates. Mixed in with the iron is a healthy amount of nickel, which is iron's quieter cousin on the periodic table. Together they form a heavy, metallic soup, but the numbers do not quite add up. The outer core is a little lighter than pure iron, and nickel should be at those pressures. So something else must be down there too. Something lighter, dissolved into the metal like sugar in tea. This missing piece is one of the oldest puzzles in deep Earth science. The candidates are a small handful of light elements. Sulfur is a favorite, oxygen is another, silicon, carbon, and hydrogen all have their supporters. Each one fits some of the evidence and fails to fit other parts. Some researchers think the outer core holds a blend of several of these, in proportions we cannot yet pin down. Others wonder whether the inner core and outer core hold different mixtures, which would explain some of the odd seismic signals we pick up. The question remains open. We are studying a chemistry experiment we can never sample. Step back, though, and the materials become even more remarkable. Every atom of iron in the core, every grain of nickel, was forged in the heart of a dying star. Long before the sun existed, an older generation of stars lived and ran out of fuel. In their final moments, they fused lighter elements into heavier ones, building iron in their cores. When those stars collapsed and burst, they scattered their metal into the cold dark between the stars. That metal drifted for ages, mixed with hydrogen and dust, and eventually gathered into the cloud that would become our solar system. When Earth formed, about 4.5 billion years ago, it grew from countless smaller bodies crashing together. The heavy metals among them sank inward, pulled by gravity, while the lighter rocks floated up to form the mantle and crust. The iron now spinning at the center of our planet is, in a real sense, ancient starlight that has finally come to rest. The same can be said for the nickel in a coin, the iron in your blood, and the steel in any nearby beam or rail. They share a common origin with the molten ocean below us. Even the lighter elements, suspected in the core, may have traveled great distances to be here. Some of the sulfur could come from grains that condensed near the early sun. Some of the hydrogen may have arrived later, carried in by icy comets or wet asteroids during Earth's chaotic early years. Those same comets and asteroids likely brought much of the water in our oceans, the carbon in our forests, and the nitrogen in the air you are breathing right now. The planet is, in a quiet way, a meeting place for materials from many corners of the cosmos. So the boundary between rock and metal is not just a line on a diagram. It is the seam where one cosmic story meets another. Above, the slow drift of silicate stone, the world of mountains and seafloors. Below, a memory of dying stars kept warm by pressure and time. We can map the boundary with seismic waves, but we cannot touch it. We can guess its recipe, but we cannot taste it. For now, the exact mixture down there remains one of the deepest unknowns in the science of our own home, hidden under thousands of kilometers of patient stone. Far below the rocky crust we walk upon, beneath the slow churn of the mantle, there flows an ocean unlike any other. It is made of liquid iron and nickel, glowing white-hot, denser than anything we touch in daily life. This metal sea wraps around the solid inner core like a thick, restless shell, and though we will never see it, we know it is in constant motion, stirred by forces that have been at work since the Earth was young. The first of these forces is heat. The center of our planet still holds warmth left over from its birth, from the violent gathering of dust and rock more than 4 billion years ago. To this ancient heat, the slow decay of radioactive elements adds a little more, like coals quietly burning in a deep hearth. Heat rises, cooler material sinks, and so the liquid metal turns over and over in lazy, enormous loops in a slow boil that has never once paused in human history. The second force is pressure, and it is almost beyond imagining. At the boundary where the liquid outer core meets the solid inner core, the weight of everything above presses down with a force more than 3 million times the air pressure at sea level. Pressure that strong changes how matter behaves. It can squeeze a liquid into a solid, even when that solid is hotter than the surface of the sun. Pressure is the quiet sculptor of the deep earth, shaping what stays fluid and what stiffens into crystal. The third force is gravity, pulling everything toward the center. Long ago, when the young Earth was still molten through and through, gravity sorted the planet by weight. The heaviest elements, mostly iron, sank inward. The lighter rocky materials floated upward. This slow settling is called differentiation, and it gave our world its layered shape. Gravity is still at work today, still pulling, still holding the dense metal ocean in place against the lighter mantle above. Then there is rotation. The Earth turns once each day, and that spinning twists everything inside it. As the liquid metal rises and falls in its convection loops, the planet's rotation bends those loops sideways into long spiraling columns. This twisting effect is known as the Coriolis force, the same gentle hand that shapes hurricanes in the sky. In the outer core, it shapes rivers of molten iron instead. The combination of heat, rotation, and flowing metal does something remarkable. It generates Earth's magnetic field, the invisible cocoon that surrounds our planet, and deflects harmful particles from space. Scientists call this process the geodynamo. The basic idea is widely accepted, but the details remain open. We do not fully know how the flow patterns organize themselves, why the field sometimes weakens and flips, or exactly how energy moves from the churning iron into the magnetic lines that reach far above our heads. Tidal forces add another small pull. The moon and sun tug gently on the Earth as they pass overhead, and that tugging does not stop at the surface. It reaches all the way down, flexing the planet ever so slightly, perhaps stirring the liquid core in subtle ways. Some researchers wonder whether these tides could nudge the geodynamo, helping shape its rhythms over long stretches of time. Others think the effect is too small to matter. The question has not been settled. There may also be chemical forces at work that we have only begun to understand. As the inner core slowly grows, freezing iron out of the liquid above, lighter elements get left behind in the fluid. These lighter ingredients then rise like bubbles in a warm pot, adding fresh energy to the convection. This idea, called compositional buoyancy, is one of the leading theories for how the geodynamo keeps itself going. Yet the exact mix of light elements remains uncertain, and so the picture is incomplete. All these forces, heat, pressure, gravity, rotation, tidal pull, chemistry, work together in the dark, far beyond any human reach. They have been working for billions of years, sculpting the iron heart of our world, drop by drop, loop by loop. They built the magnetic shield that has watched over every living thing that ever crawled, swam, or flew across this planet, and they continue right now beneath your feet while you rest. What remains open is how these forces balance over very long times. Some grow stronger as the planet cools, others may fade. The deep ocean of liquid iron is not a finished thing. It is a slow evolving system whose future shape we cannot yet predict with confidence. For tonight, it is enough to picture that hidden sea glowing quietly in the dark, stirred by ancient hands we are still learning to recognize. Tucked deep inside our planet, far below every ocean and every mountain route, sits a solid ball of metal that most of us will never picture clearly. It is roughly 760 miles in radius, give or take. That means its full width is about 1,500 miles across. To picture that, imagine the distance from New York City to roughly the middle of Texas. Now compress all of that into a single sphere of hot, dense iron and bury it under thousands of miles of rock and molten metal. The inner core is smaller than the moon. The moon is about 2,100 miles wide. So if you placed our inner core beside the moon in the night sky, the moon would be the larger of the two. And yet, this small iron ball sits at the heart of a planet that holds every ocean, every forest, every city, every living thing we know of. The whole grand stage of life rests on top of a metal sphere smaller than our nearest neighbor in space. It helps to shrink the Earth down to something you can hold. Imagine our planet as an apple resting on your kitchen counter. The thin skin of the apple would be the crust, the part where we live and build and grow our food. The thick flesh of the apple would be the mantle, the slow-moving rock that fills most of the inside. And right at the center, the apple's small core of seeds would be roughly where the iron heart sits, a quiet point at the middle of everything. Now consider the depth. To reach the top of the inner core from the surface, you would need to travel about 3,200 miles straight down. That is farther than the distance from Los Angeles to New York. If you could drive a car at highway speed without stopping, it would take you days to cover that distance on a flat road. And the road we are imagining goes straight down through rock that becomes hotter and denser with every mile. The temperature down there is its own kind of staggering. Most estimates put the inner core somewhere between 9,000 and 10,800 degrees Fahrenheit. That is roughly as hot as the surface of the sun. Picture that for a moment. The surface of our nearest star is glowing white hot in the daytime sky, 93 million miles away. And a sphere of similar temperature sits at the bottom of the planet beneath your feet, separated from you only by layers of rock and metal. The pressure is harder to imagine because nothing in daily life compares. At the center of the Earth, pressure climbs to around 3.5 million times the pressure of the air around you right now. The air pressing on your skin at sea level feels like nothing because you have always lived in it. Multiply that gentle squeeze by 3.5 million. That is the squeeze on every atom of the inner core. It is this pressure, more than the heat, that keeps the inner core solid. Iron at those temperatures would normally be liquid, even gas. But the weight of the entire planet pushing inward forces those iron atoms to lock together into a solid form. Age is another scale worth sitting with. The Earth itself is around 4.5 billion years old. The inner core, though, is younger. Some studies suggest it began to freeze into solid form somewhere between 1 and 2 billion years ago. Others propose a much more recent birth, perhaps only 500 million years ago. The honest answer is that researchers are still working it out. The numbers shift as new measurements come in. What we can say is that for much of Earth's history, there may have been no solid inner core at all, just a fully liquid metal heart slowly cooling. And the growth is almost too slow to picture. The inner core may be expanding outward by less than 1 millimeter each year as more liquid iron freezes onto its surface. A single human lifetime would add only a few inches of new metal. Over 1 billion years, that slow freezing builds up the iron ball we have today. So tonight, as you settle in, let the sense of scale wash over you gently. A solid sphere, smaller than the moon, as hot as the sun's surface, squeezed by the weight of a whole world. Older than complex life on land, perhaps, but younger than the planet that holds it. Growing drop by drop, far too slowly for any creature to notice. It is a quiet, hidden thing. And and we are only beginning to understand what it has been doing all this time. Imagine, for a moment, that you could float gently down through the layers of the Earth and pause just above the surface of the inner core. The journey would carry you through cool stone, then warm rock, then a slow-burning sea of liquid metal. And there, far below the deepest ocean trench, far below anything human hands have ever touched, you would arrive at a quiet boundary. Beneath you, a solid ball of iron and nickel would gleam in a way no human eye has ever seen. The surface of the inner core is not a place anyone can visit. It cannot be photographed. No light has ever fallen on it, and yet scientists believe they can describe it, at least in rough outline, by listening to the way earthquake waves bend and slow as they cross its edge. From those whispers, a picture begins to form. The boundary itself is sharp. On one side, liquid metal flows like a hot, heavy ocean. On the other, that same metal is locked into a solid form by the unimaginable weight of the planet pressing down from every direction. If your eyes could somehow work in that place, the colors might surprise you. The inner core is thought to glow with a fierce pale brightness, hotter at its surface than the visible face of the sun. Some estimates put the temperature near 5,000 degrees Celsius. A few studies suggest it could be even higher. The exact number remains an open question, and researchers still argue over it, using different models of how iron behaves under crushing pressure. What seems clear is that the surface would not be dark. It would shine with its own heat, a soft, steady radiance trapped forever beneath thousands of kilometers of rock. The texture of that surface is one of the most curious mysteries of all. Some researchers picture it as smooth, like the polished skin of a metal sphere. Others wonder if it might be uneven, with gentle hills and valleys carved by the slow freezing of iron from the liquid above. There are even ideas that parts of the surface grow faster than others, building outward in patches, while other regions stay still or slowly melt back into the ocean of metal. If those ideas are correct, the inner core would not be a perfect ball at all. It would have a quiet, lopsided geography of its own, shaped by forces we can barely measure. The heat down there does not behave the way heat behaves on the surface of our world. Up here, hot things rise and cool things fall, and air or water carries the warmth away. At the boundary of the inner core, the pressure is so extreme that the rules begin to bend. Iron stays solid even though it is hotter than molten lava. Liquid metal touches solid metal without boiling, without steaming, without any of the familiar drama of heat we know from kitchens or campfires. The exchange is slow, patient, almost geological in its calm. Atoms of iron drift from the liquid and settle onto the solid, one by one, across spans of time longer than any civilization. Floating just above the surface, you would feel no wind because there is no air. You would hear no sound in the human sense, though the whole region hums with the slow churn of metal currents and the faint groan of pressure. The view in every direction would be a glowing wall of bright iron below and a dimmer, swirling sea of liquid metal above. It would be the strangest beach in the universe, where a metal ocean laps against a metal shore that has never known a single drop of water. How that heat got there in the first place is still being worked out. Some of it is leftover warmth from the violent birth of our planet, when countless small worlds crashed together to form the Earth. Some of it comes from the slow decay of radioactive elements scattered through the deep interior. And some of it may be released as the inner core slowly grows, with each new layer of freezing iron giving off a small puff of heat. Which of these sources matters most is still debated. The honest answer is that we do not yet know the full recipe. For tonight, it is enough to picture that quiet, glowing boundary, a solid iron surface bathed in its own light, pressed by an ocean of molten metal, hidden beneath every footstep you have ever taken. A place no eye will ever see, but one that shapes the world above in ways we are only beginning to understand. Now we sink even deeper into the question, down past the molten ocean of iron, toward the solid heart at the very middle. The inner core is there, a sphere of metal, larger than the moon. But how did it get there? How did a solid ball form inside a planet that was once entirely molten? This is one of the quietest puzzles in Earth science, and the answers we have are still partial. Long ago, when the Earth was very young, the whole planet was hot. Heat came from the impacts of forming, from the squeeze of gravity pulling matter inward, and from the slow decay of radioactive elements buried in the rock. The interior glowed. The metals, being heavy, sank toward the center. The lighter, silicate rocks floated upward and became the mantle and the crust. This sinking of iron toward the middle is sometimes called the iron catastrophe, though the word catastrophe is misleading. It was not sudden. It was a long, slow settling that may have taken tens of millions of years. For a long stretch of Earth's history, the entire core was liquid. No solid ball sat at the center. The metal at the middle was hot enough and under such steady conditions that it stayed fluid. Then, at some point, the inner core began to freeze into being. Not freeze in the way ice forms on a winter pond, but freeze in the deep sense of a liquid turning solid. The pressure at the center is so immense that iron there can solidify even at temperatures hotter than the surface of the sun. When did this freezing begin? That is one of the open questions. Some studies suggest the inner core started forming around 1 billion years ago. Other studies push the date back much further, perhaps 2 or 3 billion years. A few researchers wonder if it could be even younger, only 500 million years old. The evidence comes from indirect clues. Tiny grains of ancient rock carry magnetic signatures from the time they cooled. By studying these signatures, scientists try to read the strength of the Earth's magnetic field across deep time. A sudden change in that strength might mark the moment the inner core began to crystallize. But the readings are faint, the rocks are rare, and the interpretation is not settled. The picture most researchers hold is this: as the Earth slowly lost heat to space over billions of years, the temperature at the very center finally dropped just enough for iron atoms to lock together into a solid lattice. A tiny seed of solid metal formed. Then, layer by layer, more iron crystallized onto that seed. The inner core has been growing ever since, adding perhaps 1 millimeter of new solid metal each year. Over geologic time, that small rate builds a world. But the simple picture has problems. Iron alone, under the conditions at the center of the Earth, may not freeze easily. It seems to need a kind of nudge, a starting point. In a perfectly pure liquid, atoms can stay liquid even below their normal freezing point if there is nothing to begin the crystal. This is called supercooling. Some researchers wonder how the inner core ever began at all, since the conditions deep inside the planet may have favored supercooling for a long, long time. One idea is that some other element mixed in with the iron gave it a place to start. Another idea is that turbulence in the molten core created the right conditions by chance. The truth is uncertain. There is also the question of what the inner core looked like when it was young. Was it a smooth, growing ball, or did it form in patches with crystals knitting together unevenly? Some recent studies suggest the inner core may have grown faster on one side than the other, leaving it slightly lopsided even today. Why one side would grow faster is itself a mystery. Perhaps heat escapes more easily through certain regions of the mantle above, drawing crystallization downward in those zones. Perhaps the difference is older than we can presently trace. What we can say with confidence is that the inner core is not a permanent feature of the planet. It had a beginning, it has been growing, and it carries within it a record of the Earth's slow cooling, a record we are only beginning to learn how to read. Each new measurement, each new earthquake studied from a different angle gives us another faint glimpse. The story of how this solid heart came to be remains, for now, a tale told in fragments. We sit with those fragments tonight, listening to a deep, slow process still unfolding far below. The Earth turns once each day. That much we can feel, even if we cannot sense the motion itself. The ground beneath us moves with us. The seas, the air, the mountains, all of it spins together at the same steady pace. But far below, near the very center of our world, something else may be turning in its own rhythm. The inner core, that solid ball of iron, may not spin in perfect step with the rest of the planet. This idea is called differential rotation. It means the inner core moves a little faster or a little slower than the ground we walk on. The difference is tiny. We are not talking about a wild runaway spin. We are talking about fractions of a degree per year, sometimes less, but across long stretches of time, those small drifts add up. Over decades, the inner core may shift by a noticeable angle relative to the crust above it. The first hints came in the 1990s, when scientists studied seismic waves that passed through the core. They noticed that waves traveling along certain paths seemed to arrive a little sooner over the years. The change was small, but it was steady. One way to explain it was that the inner core was slowly rotating, carrying its inner structure to a new position. The waves were not changing. The thing they were passing through was this was a strange and beautiful idea. A whole planet within our planet turning at its own pace, hidden by thousands of miles of rock and liquid metal. For a while, many researchers accepted it as the best explanation. The inner core, they said, was spinning slightly faster than the surface. A superrotation, some called it, but the story has not stayed simple. More recent studies have offered a different picture. Some seismic data suggests that the inner core's spin is not constant at all. It may speed up, then slow down, then perhaps even pause. One group of researchers proposed that around the year 2009, the inner core's rotation relative to the surface came nearly to a stop. After that, they suggest it may have begun to drift in the opposite direction. Other scientists are not so sure. They look at the same data and see something else. Maybe the change is real. Maybe it is an illusion caused by tiny shifts in the core's surface rather than its rotation. The truth is, we are watching a ghost move through a fog. The signals are faint, the instruments are sensitive, but the journey those signals make is long. They pass through layers of rock, through the liquid outer core, through the boundary, and into the solid sphere at the center. Then, back out again. Any small change along the way can mimic the change we are trying to measure. What is fascinating is that the inner core may have its own cycle. Some studies suggest a rhythm of around 70 years, a slow back and forth, like a deep mechanical pendulum buried at the heart of the world. If true, the inner core would speed ahead for decades, then slow, then drift back, then begin again. This rhythm might leave fingerprints on the surface, tiny changes in the length of the day, faint shifts in the magnetic field, even slow changes in sea level, some have suggested. None of these links are proven. They are open threads waiting to be pulled. It is strange to think that the day itself might not be exactly the same length each year. The Earth's rotation does wobble ever so slightly. Sometimes a day is a millisecond longer, sometimes a millisecond shorter. Some of this comes from the oceans and the atmosphere, but some of it, researchers think, may come from the deep coupling between the inner core, the liquid iron around it, and the mantle above. They tug on each other. They exchange a kind of slow momentum. When one shifts, the others respond. We cannot yet say which model is correct. The super-rotation idea, the oscillation idea, the near-pause idea, all of them are still in play. Each is built on careful work. Each captures a piece of the puzzle. None of them, on their own, explains everything. So tonight, as you settle in, picture that motion far below. A solid iron sphere, quietly turning at its own pace. Sometimes leading, sometimes lagging, sometimes nearly still. A spin within a spin, governed by forces we are only beginning to read. The rhythm is there. We can feel its echoes. We just cannot yet hear the music in full. Far above the spinning iron heart of our world, something invisible reaches out into space. It stretches past the clouds, past the highest satellites, past the orbit of the moon. It bends around our planet like a soft cocoon, shaped by the slow churn of liquid metal far below. We call it the magnetic field. And though we cannot see it with our eyes, we owe nearly everything to its quiet presence. The story begins back at the core. As the liquid iron of the outer core moves and swirls, it carries electric charges along with it. Moving charges create magnetism. So the slow churning ocean of metal beneath our feet acts like a giant generator, pumping out a magnetic field that reaches far beyond the planet itself. Scientists call this process the geodynamo. The name sounds grand, but the picture is simple. Hot metal rises, cool metal sinks, and the spinning Earth twists it all into a long looping pattern that escapes through the rocks above. What we see at the surface is only the faintest hint of this hidden engine. A compass needle tilts gently north. Birds, turtles, and certain fish seem to feel the field and use it to find their way across vast distances. The aurora glows green and pink near the poles when particles from the sun strike the upper air, guided there by invisible magnetic lines. Each of these small, beautiful things is a whisper from the core. The field also acts as a shield. The sun sends out a steady stream of charged particles called the solar wind. Without protection, this wind would slowly strip away our atmosphere, drying the planet over long stretches of time. The magnetic field deflects most of these particles, curving them around the Earth like a river flowing around a stone. Some leak through near the poles, which is why the auroras dance there. The rest are swept harmlessly into space. So the iron at the center of the Earth, more than 4,000 miles below the surface, helps protect the air we breathe. The connection feels almost impossible to believe. A solid ball of metal we have never touched, surrounded by an ocean of liquid metal we will never see, somehow shapes the sky above our heads. Yet the connection is not perfectly understood. Researchers can describe the general picture of the geodynamo, but the details remain slippery. Computer models of the core's flow are improving each year, but they still cannot match every feature of the real field. The strength of the field has been weakening slowly over the last 2 centuries by a small amount each decade. One possibility is that this is part of a normal cycle, a gentle rise and fall that has happened many times before. Some researchers wonder if it signals something larger, perhaps a slow shift in the patterns deep below. The evidence is incomplete, and no one can yet say which view is closer to the truth. There is also a strange weak spot in the field, sitting above part of the South Atlantic Ocean. There, the protective shield dips lower than elsewhere, and satellites passing through must take extra care. The cause is thought to lie in unusual flow patterns in the outer core, perhaps linked to a dense region of rock that sits at the very bottom of the mantle, just above the molten metal. The exact reason remains an open question. We see the dip clearly. We can map it from orbit. But the conversation between the deep Earth and the field above is one we are still learning to read. Other planets tell us how unusual our situation may be. Mars once had a magnetic field, but it faded long ago, and the planet now sits exposed to the solar wind. Venus has almost no global field at all. The gas giants have powerful fields generated in ways we are still piecing together. Earth's combination, a solid inner core, a churning liquid outer core, and a magnetic shield that has lasted for billions of years, may be common, or it may be rare. We do not yet know. So when you look up at the night sky, the empty space between you and the stars is not quite empty. It hums with the soft pressure of a field born deep in the earth. The compass on a hiker's wrist, the bird flying south for winter, the soft green glow above the Arctic, all of them are listening to the same quiet voice. A voice that begins in a place no human has ever visited. A voice whose source we still do not fully understand. And tonight, far below you, the iron continues to hold. The magnetic poles of the Earth are not where most people think they are. They are not fixed points. They are not painted onto the globe. They drift slowly and constantly, like quiet swimmers in a vast dark pool. The North Magnetic Pole, the one that pulls the needles of compasses, sits nowhere near the geographic top of the world, and it moves year after year, decade after decade. It wanders across the Arctic, sometimes slowly, sometimes with surprising speed. For most of the 20th century, the North Magnetic Pole drifted at a gentle pace, only about 10 kilometers each year. Then, sometime in the 1990s, something changed. The pole began to accelerate. By the early 2000s, it was moving at roughly 50 kilometers per year, racing across the Canadian Arctic and heading towards Siberia. No one is entirely sure why. The most common idea is that deep beneath our feet, two competing patches of magnetic field at the core boundary are battling for dominance, with the Siberian patch slowly winning. But that explanation, while elegant, remains a working theory rather than a settled answer. The South Magnetic Pole drifts too, though more slowly, off the coast of Antarctica, hundreds of kilometers from the geographic south. The two poles are not perfect mirrors. They do not move in step. They do not sit opposite each other across the planet. The magnetic field is lopsided, lumpy, and full of quiet asymmetries that we still cannot fully explain. The extremes of this hidden system are difficult to picture. Consider the speed. 50 kilometers in a single year is, by the standards of solid Earth, astonishingly fast. Continents drift at the pace of growing fingernails. Mountains rise over millions of years. Yet the magnetic pole, born of the swirling liquid iron far below, can shift across the polar ice in a human lifetime. Some scientists wonder whether we are witnessing a pulse of unusually active flow in the outer core. Others suspect we are simply catching a glimpse of normal behavior we never had the instruments to measure before. Then there is the weakening. Over the last 2 centuries, the total strength of Earth's magnetic field has dropped by roughly 9%. This is measurable, real, and ongoing. Whether it signals something dramatic, like the beginning of a slow reversal, or whether it is a small wobble in a long and noisy history, no one can yet say with confidence. The field has been weaker in the past. It has been stronger. The averages we draw are based on a sliver of recorded time. One of the strangest features sits over the South Atlantic. There, the magnetic field is unusually faint, forming a region known as the South Atlantic Anomaly. Inside this zone, the protective shield thins, and satellites passing overhead encounter more radiation from space. The anomaly is growing. It is also splitting, with hints of a second weak spot forming nearby. Some researchers believe this region reflects a strange reverse polarity patch deep at the core boundary, churning against the surrounding flow. Others suspect it is a temporary feature that will fade. The honest answer is that we do not yet know. The most extreme behavior of all, though, may be the wandering itself. The poles do not simply drift in straight lines. They loop, they pause, they sometimes reverse direction for years before resuming their old path. Records pulled from ancient lava flows, where iron particles froze into place pointing toward the magnetic pole of their day, suggest that this wandering has been going on for as long as the field has existed. The pole has visited places no living person has ever seen it. It has stood at times near the equator. It has, on rare occasions, swapped ends entirely with its southern partner. What makes these extremes so quietly remarkable is that they all trace back to a place we cannot reach. The liquid iron ocean turning beneath the mantle, the solid inner ball spinning at its heart, the slow churn of heat rising from below. Every twitch of the compass needle is an echo of motion thousands of kilometers down. We are watching the surface ripples of a storm we will never directly see. For tonight, picture the magnetic pole as a faint blue glow, drifting across the white silence of the Arctic. It moves while you sleep. It moved while your grandparents slept. It will move while children not yet born are dreaming. The reasons remain a puzzle. The pattern remains incomplete. And the deep iron heart of the planet keeps turning, indifferent to our questions, writing its own slow and unfinished story across the face of the world above. There is a strange and beautiful detail hidden in the rocks beneath our feet. Long ago, when certain rocks were still molten, tiny grains of iron inside them lined up like compass needles. They pointed toward the magnetic pole of that ancient time. When the rock cooled and hardened, those grains froze in place. They became a kind of memory, a fossil of the magnetic field as it was on the day that stone was born. When scientists first read these stone memories, they found something quiet and strange. The needles did not always point the way they point today. In some rocks, the tiny iron grains pointed the opposite direction. North was south. South was north. The field had flipped, and not just once, but many times across the long history of the planet. This is the mystery of the reversal. The magnetic shield around the Earth, born from the slow churn of liquid iron deep in the outer core, does not stay the same forever. It wobbles, it weakens, and sometimes, every few 100,000 years on average, it turns itself upside down. The last full reversal happened about 780,000 years ago. The next one, no one can say. It might begin tomorrow in some slow geological sense, or it might wait another 100,000 years. What makes this so quietly puzzling is that the reversals do not seem to follow a clock. They are not regular. Sometimes, the field stays calm for tens of millions of years, holding one direction for an unimaginable stretch. Other times, it flips again and again within a shorter span. Scientists have built timelines from rocks all over the world, matching ancient lava flows in Iceland with ones in Hawaii. In Africa, in the deep sea floor, the pattern that emerges looks almost random, like rainfall on a window, with no rhythm anyone has yet decoded. One idea is that the reversals begin as small disturbances in the swirling iron of the outer core. A patch of flow turns the wrong way. The patch grows. It tugs at the larger field. Eventually, the whole shape of the magnetic field becomes tangled, weakens, and then settles into a new direction. In this view, a reversal is a kind of slow accident, an emergent hiccup of fluid motion no one can predict in detail. Another possibility is that something in the deep mantle, the thick rocky layer above the core, nudges the timing. Cold slabs of old ocean floor that have sunk down for hundreds of millions of years may be resting now against the outer core. They draw heat out unevenly. That uneven cooling could shape the patterns of iron flow below, perhaps making reversals more likely in some eras than others. Other researchers wonder if the inner core itself plays a role, with its slow growth subtly tuning the dynamo above it. The evidence is incomplete on all sides. What the rocks tell us, in their quiet way, is that a reversal is not a sudden event. It is a slow fading. Over thousands of years, the field weakens. It splits into several poles at once, scattered across the globe like loose magnets on a table. Then, gradually, the new pattern firms up, and a single north and south return, only swapped. During the long fade, the shield around the planet is thinner. More cosmic particles reach the upper air. The auroras may dance over places that have never seen them. There is a particular beauty in this. The rocks that hold these stories are often ordinary looking. A piece of dark basalt from an old lava flow. A core of sediment pulled from the deep ocean floor. Inside them, in grains too small to see, lies a whisper from a vanished version of the planet, when compasses, had they existed, would have pointed the wrong way. Scientists today watch a slowly weakening patch of the modern field, a wide, low-strength region drifting beneath the South Atlantic. Some wonder if it is the first hint of a coming reversal. Others think it is just a normal wobble that will pass. There is no way to know for certain. The deep iron does what it does on its own quiet schedule, and we are only beginning to listen. So when you picture the inner core tonight, picture also this slower dance above it, a field that breathes in and out across hundreds of thousands of years, a shield that has flipped countless times in the planet's long life and will flip again in some far-off century no one alive today will see. The needles in the ancient stones remember. The core, in its silent way, keeps writing the next chapter. Long before anyone could see inside the Earth, people were already trying to guess what lay beneath their feet. They dug wells. They climbed into caves. They watched volcanoes pour molten rock onto the land and wondered where all that fire came from. For most of human history, the deep Earth was a kind of dream space filled with imagined oceans and underground worlds. The truth, when it finally began to arrive, came not from digging, but from listening. In the late 1800s, a few quiet thinkers began to notice something strange about earthquakes. When the ground shook in one place, sensitive instruments far away would shake too. But only after a delay. The waves were traveling through the Earth itself. By timing how long they took to arrive, scientists realized they were holding a kind of map in their hands, a map drawn by sound moving through stone. The early seismographs were simple machines. A weight hung from a frame, a pen pressed against a slowly turning drum of paper. When the ground moved, the pen wobbled, and a record was made. These devices were delicate, often built in basements where the air stayed still. From these humble tools came one of the greatest discoveries in the history of science. In 1906, a British geologist named Richard Dixon Oldham studied the wiggles on these paper records. He noticed that certain waves from distant earthquakes seemed to vanish on the far side of the planet. They entered the Earth, traveled partway through, and then disappeared. Oldham proposed that something deep inside must be blocking or bending them. He suggested, for the first time, that the Earth had a core. The idea was bold. No one had ever seen this core. No one ever would. But the math of the missing waves was hard to argue with. Other scientists picked up the thread, refining the picture year by year. They began to suspect that the outer part of this core was liquid, because certain kinds of waves, called shear waves, could not pass through it. Shear waves need a solid to travel. Their absence pointed to an ocean of melted metal far below. Then, in 1936, a Danish seismologist named Inge Lehmann made the next great leap. She was studying records of a strong earthquake that had struck New Zealand. While tracing how its waves bent and bounced inside the Earth, she found a pattern that puzzled everyone. Some waves were appearing where they should not have been. They were arriving in a kind of shadow zone, as if something solid deep inside the liquid core was redirecting them. Lehmann proposed that the core had a core, a solid inner ball suspended inside the molten outer layer. She published her idea in a short paper with the simple title, P prime, referring to the wave she was studying. It took years for other scientists to accept her conclusion, but eventually, the evidence piled up. The inner core was real, a hidden iron world, discovered not with a shovel or a telescope, but with patient listening. Once scientists knew the inner core existed, they began asking what it was made of. Iron seemed likely, since iron is common in the cosmos and dense enough to settle at the center, but pure iron alone did not quite match the speed at which seismic waves passed through the core. Something else had to be mixed in. Lighter elements, perhaps. The recipe is still debated today. As tools improved, researchers found something even more surprising. The waves moved through the inner core at different speeds depending on the direction they traveled. Faster from pole to pole, slower along the equator. This hinted that the iron inside was not a jumble of tiny crystals, but might be arranged in vast, ordered structures. Some researchers think these structures could be enormous single crystals, possibly stretching for hundreds of kilometers. Crystals nearly the size of continents, locked at the heart of our planet. Others suggest the picture is more complicated, with patches of different textures or layers stacked in unexpected ways. The question is still open. We cannot reach into the core and pull out a sample. We can only study the echoes that earthquakes send through it, slowly building a picture from waves that have traveled where no human ever will. It is humbling to consider. The story of how we learned about the inner core was not written by explorers crossing oceans or astronauts crossing space. It was written by quiet people in quiet rooms, watching pens trace lines on paper, asking what the lines might mean. From those gentle scratches came the knowledge that a vast metal heart beats inside our world, slowly turning in the dark. For most of the past century, the inner core seemed like a single thing, a solid iron ball, hot and dense, sitting quietly at the center of the Earth. That picture was already strange enough. But around the early 2000s, something in the seismic data began to whisper that the picture was not quite complete. Hidden inside the solid inner core, there might be another layer, a core within the core, an innermost heart we had never imagined. The idea came from a careful look at how seismic waves pass through the deepest part of the planet. When a large earthquake shakes the crust, its waves travel in all directions. Some plunge straight through the center. By the time they reach the other side of the world, they carry tiny clues about everything they touched along the way. Researchers studying these waves noticed something odd. Waves passing through the very center seemed to behave a little differently from waves passing through the outer parts of the inner core. The change was small, but it was there. One possibility is that the iron crystals in the deepest region are lined up in a different direction. In the outer part of the inner core, the crystals appear to align mostly along the axis that runs from pole to pole. In the inner core, if it exists, they may tilt toward a different angle, perhaps closer to the equator. Why this would happen is far from settled. Some researchers wonder if it points to two separate stages in the core's long history. The outer layers may have frozen under one set of conditions. The deepest layers may have formed earlier, when the young Earth was a different place entirely. Other scientists are not yet convinced the inner core is real. They argue that the strange wave patterns might come from quirks in the path the waves take, or from variations along the boundary between the inner and outer core. The signal is faint. The data is rare. Only certain earthquakes picked up by certain stations on the far side of the planet can even test the idea. So the question hangs in the air, unresolved. Either there is a hidden ball of differently aligned iron about 600 kilometers across at the very middle of our world, or there's not. We have not yet ruled it out, and we have not yet confirmed it. What makes the idea so strange is the scale of the thing. If the inner core is real, it is roughly the size of a small moon, tucked inside an ocean of liquid metal, tucked inside a mantle of slowly creeping rock. Layer upon layer, each one different, each one hidden from any direct view. And the only way we can even guess at the innermost layer is by listening to the faint shiver of distant earthquakes after they have passed through almost the entire Earth. There are other counterintuitive details about the core that surprise even the researchers who study it. The solid inner core is hotter than the surface of the sun, yet it stays solid because of the crushing pressure that holds its atoms in place. The liquid outer core, just above it, is cooler but flows freely because the pressure there is lower. So as you travel inward, you pass from solid rock to liquid metal to solid metal again. with the hottest part sitting at the very center. The usual rule that hotter things melt and cooler things freeze gets turned on its head once pressure enters the picture. The inner core may also be slightly lopsided. Some studies suggest that its eastern half and its western half are not quite the same. One side may be growing a little faster. The other side may be slowly melting back into the liquid above it. If this is true, the inner core is not a calm, symmetrical sphere, but a quietly uneven shape, gaining material in one place and losing it in another. The cause is unclear. It may have something to do with how heat escapes through the mantle far above. It may have other reasons we have not yet imagined. So the simple story of a single solid ball turns out to be only the first chapter. Beneath it may lie a second ball with a different grain. Around it may lie a slow imbalance. And inside all of it, pressure rewrites the usual rules of hot and cold, solid and liquid. The deeper we listen, the stranger the center of our own planet becomes, and the more questions seem to gather in the dark beneath our feet. To stand at the surface of the Earth is to live inside a gentle squeeze. The air above us presses down with a soft, steady weight, and we never feel it because our bodies push back with the same force. But that weight is only the beginning of pressure. Dive into the ocean, and every 10 meters of water adds another full atmosphere of squeeze. Go a kilometer down, and the pressure would crush a human lung in seconds. Now imagine traveling not 1 kilometer, but more than 6,000 straight down into the planet itself. At the center of the Earth, the pressure climbs to something almost impossible to picture. It reaches more than 3.5 million times the pressure of the air at the surface. Iron, which feels heavy and stubborn in your hand, behaves there in ways it never behaves up here. It stays solid even at temperatures hot enough to vaporize it on the surface. The squeeze itself holds the atoms in place, packed so tightly together that they form a crystal structure denser than almost anything else on the planet. This pressure connects the core to everything above it, like a single long note holding up a piece of music. The weight of the mantle, that thick layer of hot rock between the crust and the core, presses down on the liquid outer core. The liquid outer core, in turn, presses on the solid inner ball at the very middle. Every grain of sand on a beach, every mountain, every drop in every ocean adds a tiny share to that crushing weight. Take any of it away, and the balance shifts. The connections run upward too. The pressure deep inside helps decide how the liquid iron flows. The flow of that liquid iron generates the magnetic field. The magnetic field reaches out into space and shields the atmosphere from the solar wind, that endless stream of charged particles blowing off the sun. The atmosphere then protects the oceans, and the oceans help shape the climate, and the climate shapes the life that walks the surface. A single chain runs from the squeezed iron at the center to the soft breath in your lungs tonight. Researchers try to study this extreme pressure in laboratories using tiny diamond anvil cells, devices that pinch a sample of iron between 2 diamond tips. With enormous force squeezed into a microscopic point, they can briefly reach pressures close to those at the core. What they find raises more questions than it answers. Iron at such pressure may form different crystal shapes depending on how it is squeezed and heated. Some experiments suggest one structure. Other experiments suggest another. The true arrangement of atoms at the center of our planet remains an open puzzle. One idea is that the iron crystals at the center line up in long columns, all pointing roughly along the axis of the Earth's spin. Another possibility is that the crystals are layered like the pages of a book, stacked in patterns shaped by the slow flow of heat. A third possibility is that the inner core has different regions with different arrangements, as if it were a quilt sewn together from many fabrics. We do not yet know which picture is closest to the truth. What we do know is that the pressure shapes how seismic waves travel. When earthquakes ring through the planet, the waves move faster along one direction than another, as if the core itself has a grain, like wood. That grain is one of our few clues. It hints that the squeeze and the spin and the slow cooling have all worked together to organize the iron in ways we are still learning to read. The connections reach even further. The same pressure that holds the inner core solid also keeps the outer core liquid at its higher level, because temperature and pressure together decide whether a metal flows or freezes. Change one, and the other matters more. Lower the pressure even a little, and the boundary between solid and liquid would shift. The whole symphony of magnetism, heat, and motion depends on this delicate agreement between forces. For now, the inner core sits at the bottom of a pressure column that runs from the soles of your feet all the way down. Each layer leans on the next, each one held by the weight of everything above. The result is a quiet, steady stillness at the heart of a moving planet. A stillness so extreme that solid metal behaves like stone, and stone behaves like syrup, and syrup behaves like ocean. How exactly all of it fits together remains one of the deepest unanswered questions about the world beneath our feet, a question we carry with us into sleep. Far below us, in the deep stillness at the center of the planet, something is slowly happening. The solid iron heart of the Earth is growing. Not quickly, not in any way you could ever see or feel, but year by year, millennium by millennium, the inner core is getting larger. The process is gentle and patient. At the boundary between the solid inner core and the liquid outer core, hot metal slowly gives up its heat. As it cools, tiny grains of iron freeze onto the surface of the solid ball. Layer after layer, the inner core thickens from below. The liquid ocean of metal above it shrinks by the same amount, drop by drop, over spans of time the human mind can barely hold. How fast does this happen? The honest answer is that we are not sure. One common estimate suggests the inner core grows by about 1 millimeter each year. On average, that is roughly the thickness of a fingernail clipping, added to a ball more than 2,000 kilometers across. Other studies suggest the growth may be uneven, faster on one side than the other. Some researchers wonder if the eastern half of the inner core freezes more quickly, while the western half slowly melts back into the liquid above. The question remains open. If the slow growth is real, then the Earth we stand on is not the same Earth that existed 1 billion years ago. Back then, the inner core was smaller. Some scientists think it may not have existed at all for much of our planet's early history. The whole core may have been liquid once, a churning sphere of molten metal with no solid heart at all. Then, at some point, the center cooled enough for the first crystal of iron to form. From that tiny seed, the solid core began to grow. When did that first crystal appear? Estimates vary widely. Some studies place the birth of the inner core at around 1 billion years ago. Others suggest it could be much older, perhaps as far back as 3.5 billion years. The evidence is incomplete. Tiny clues hidden in ancient rocks hint at changes in the planet's magnetic field, and those changes may mark the moment when the inner core first began to freeze. But the rocks are old, the signals are faint, and different teams read them in different ways. What is happening right now, beneath our feet, is part of that same long story. Heat is leaking out of the core into the rocky layer above it. The mantle, that thick shell of slow-flowing stone, carries the heat upward over hundreds of millions of years. As heat escapes, the deep ocean of liquid iron loses energy. The cooling at the inner boundary continues. The solid ball keeps growing, one delicate layer at a time. This slow growth is not just a curiosity. It may be one of the things that keeps our planet alive in a quiet, hidden way. When iron freezes onto the inner core, it releases a small amount of heat, and it also pushes lighter elements upward into the liquid layer. Those rising elements stir the molten metal. The stirring helps drive the great churning motions that generate the Earth's magnetic field. Without the slow freezing at the center, the field above us might be weaker, or different, or perhaps gone. The connection is real, but the details are still being worked out. Some researchers wonder whether the growth itself has been steady, or whether it has come in pulses. Maybe the core grew faster during certain ages of the planet, and slower during others. Maybe small bursts of freezing match up with shifts in the magnetic field recorded in ancient lava. There are hints in the data, but no agreement yet. The deep Earth keeps its history close. There is something soothing about a change this slow. While we sleep, while empires rise and fall, while continents drift across the face of the planet, the iron heart simply grows. Not by meters, not by inches, but by amounts so small that 1,000 years adds only a meter to its radius. And yet, given enough time, that quiet growth has built a solid ball larger than the moon's core. The mystery sitting with us tonight is one of pace and patience. Exactly how fast is the inner core growing now compared to 1 billion years ago? Whether it grows evenly on all sides or lopsided, whether it freezes in steady drips or in slow, uneven waves. These questions belong to a future generation of careful listeners. For now, we can rest in the knowledge that something very old, very deep, and very slow is still becoming. Iron alone cannot explain the core. When researchers measure how fast seismic waves travel through the deep Earth, the numbers come back a little lighter than pure iron should allow. The outer core, in particular, seems less dense than a liquid made only of iron and nickel would be. Something else is mixed in, something lighter, and no one is quite sure what. This puzzle has a quiet name. Scientists call it the light element problem. The core is mostly iron, with a smaller share of nickel, but roughly 5 to 10% of its mass appears to be made of lighter ingredients. The exact recipe remains one of the oldest open questions in deep Earth science. To picture why this matters, imagine the glow of molten metal in a foundry. Pure iron, melted, has a certain shine, a certain weight, a certain way of carrying sound through itself. The liquid outer core does not quite match that signature. The waves move a touch too quickly. The density falls a touch too low. Some lighter atoms must be dissolved in the iron, the way salt dissolves in warm water, changing the bulk behavior. In subtle ways, the list of suspects is short, but each one tells a different story about how Earth came together. Sulfur is one possibility. If sulfur slipped into the core during its formation, it would dim the metal slightly and lower its density in ways that match some seismic readings. Oxygen is another candidate. Under the crushing pressure near the core, oxygen can bond with iron in ways it never could near the surface, forming compounds that no human hand has ever touched. Silicon is a third possibility, and a strong one. Earth's rocky outer layers are rich in silicon, and some researchers think a portion of it sank down with the iron during the planet's molten youth. Carbon and hydrogen each have their advocates too. A trace of carbon would shift the core's properties one way. A trace of hydrogen, locked in under unimaginable pressure, would shift them another. The truth may well be a blend. Several light elements, each in small amounts, mixing together in the dark. The problem is that we cannot reach in and take a sample. The deepest hole humans have ever drilled barely scratched the upper crust. Everything we know about the core's chemistry comes from indirect signals, the speed of seismic waves, the wobble of the planet's spin, laboratory experiments that squeeze tiny flakes of iron between diamond anvils to mimic the pressures below. Each method gives a partial answer. None give a complete one. Light plays a strange role in this hidden chemistry, even though no light ever reaches the core itself. In laboratories, researchers shine intense beams of X-rays through pressurized samples of iron mixed with sulfur, or oxygen, or silicon. The way the X-rays scatter reveals how the atoms are arranged. From those patterns, scientists try to guess which mixtures behave the most like the real core. It is a kind of detective work done with photons. We use light at the surface to imagine a place where light has never been. The colors of this imagined world are worth lingering on. If you could somehow stand at the edge of the outer core and see it, the metal would not look the way molten iron looks in a forge. The pressure is too great. The temperature is too extreme. The liquid might glow with a brightness closer to the surface of a star than to any furnace on Earth. White hot, perhaps with a faint blue cast, the light pressed flat by the weight of 3,000 kilometers of rock above, and mixed into that searing glow, invisible to any imagined eye, would be these whispering traces of lighter elements, atoms that drifted down billions of years ago and never came back. The recipe matters because it shapes everything else. The exact mix of light elements changes how heat moves through the core. It changes how the magnetic field is generated. A core flavored with sulfur behaves differently than a core flavored with oxygen. Until we know which ingredients are truly there, our models of the planet's deep engine remain sketches rather than portraits. Several theories sit beside one another, none yet proven. Some studies favor oxygen as the dominant light element. Others lean towards silicon. Still others suggest the mixture has changed over time, with different elements settling out at different stages of Earth's long cooling. The evidence is partial, the answer waits below, and so the iron heart of our world keeps its small secret. Something light is hiding inside the heavy, something we have not yet learned to name. The deep Earth is not silent. It hums, it groans, it rings like a bell when a great quake passes through it. Every tremor on the surface sends waves curling down into the rock, and those waves carry sound. Sound we cannot hear with our ears, but sound all the same. Scientists slow these signals down, stretch them out, and turn them into something the human ear can almost recognize. The Earth sings in long, low tones, a slow choir of stone and metal, whose melody we are only beginning to learn. Among the strangest notes in this song is the one that tells us about heat. The core is hot, that much we know, but exactly how hot it burns, deep at its iron heart, remains one of the most stubborn open questions in all of Earth science. The numbers most often given sit somewhere between 5,000 and 6,000 degrees Celsius, roughly the temperature of the surface of the sun. Yet the true value drifts depending on which method you trust, and each method speaks in a different voice. One voice belongs to the seismic waves. When a quake rings the planet, the waves travel faster through hot rock in some ways and slower in others. The speed at which they pass through the boundary between liquid outer core and solid inner core tells us something about the melting point of iron under pressure. If we know the melting point at that depth, we know the temperature there must sit just above it on the liquid side and just below it on the solid side. The waves whisper a number. The number is not precise. Another voice belongs to the laboratory. Researchers squeeze tiny flakes of iron between two diamond tips, pressing them with forces that mimic the crushing weight of the deep earth. Then they heat the sample with lasers and watch for the moment it melts. These experiments are delicate, almost impossibly so. A flake of iron the width of a hair, pressed to pressures found nowhere else on the planet, glowing under a laser beam. The melting points measured this way have varied widely over the years. Some teams report numbers near 5,000 degrees. Others report numbers closer to 6,500. The disagreement is not small, and it has not gone away. A third voice comes from computer models. These simulations follow individual iron atoms as they jostle and slide under pressure, predicting where the solid gives way to liquid. The math is beautiful, the assumptions many. The models tend to agree with some experiments and disagree with others. No single approach has yet won the argument. So, we are left with a strange situation. We know the core is roughly as hot as a star's surface. We do not know the exact temperature within 1,000 degrees. 1,000 degrees is a lot of uncertainty for a place we claim to understand. It is the difference between a quietly cooling iron ball and a more restless one, between a magnetic field that has hundreds of millions of years left in it and one with a very different future. The temperature matters because heat is the engine. Heat moving from the inner core outward through the liquid metal ocean is what stirs that ocean into motion. The motion is what generates the magnetic field that shields us. If we do not know the temperature, we do not fully know the engine. We can hear it running. We cannot quite read the gauge. Some researchers wonder whether the core contains pockets of different temperature, regions slightly hotter or slightly cooler than their surroundings. Seismic studies have hinted at uneven patches near the boundary, places where waves slow or quicken in ways that simple maps cannot explain. One possibility is that the liquid core is not perfectly mixed, that warm plumes rise and cool sheets fall, much like the weather of an ocean we will never see. Another possibility is that the patches are something else entirely, chemical differences perhaps, or shifting crystal structures. The question remains open. When you listen to a recording of the Earth's deep hum, slowed and tuned for human ears, it sounds a little like a distant wind, a little like a long sigh. It is the sound of a planet that has been cooling for 4.5 billion years and will keep cooling for billions more. Inside that sound, somewhere, is the true temperature of the iron heart. We have not yet learned to read it cleanly. We are still listening. The song goes on beneath your feet tonight, low and patient, holding its secret close, waiting for instruments that have not yet been built and minds that have not yet asked the right question. There is a kind of beauty in the numbers that describe the deep Earth. The inner core is a ball of iron about 1,220 kilometers in radius, sitting at the very center of our planet. The whole Earth turns once every 23 hours, 56 minutes, and 4 seconds. That number is so steady that we can predict the position of stars in the sky 1,000 years from now. But the inner core, hidden far below the surface, seems to follow a slightly different beat. For many years, scientists wondered if the inner core might spin a little faster than the rest of the planet. The idea came from a simple observation. When earthquake waves pass through the core along the same path, decades apart, they sometimes arrive at slightly different times. The difference is tiny, often less than a single second. But a second of difference, measured across the whole planet, can mean the iron heart has slowly rotated to a new position. The math behind this is gentle and surprising. If the inner core were spinning faster than the rest of Earth by even a fraction of a degree each year, over decades, it would add up to a measurable shift. Early studies suggested it might gain about 1 extra turn every few hundred years. Later studies found a much smaller number, closer to a fraction of a degree per year. Some studies found almost no extra rotation at all. The numbers refused to settle. Then came a more recent puzzle. Some researchers looked at earthquake records spanning the last 60 years and noticed something strange. The inner core seemed to speed up for a while, then slow down, then almost match the rest of the planet, then perhaps drift the other way. One possibility is that the inner core wobbles back and forth on a long, slow cycle, maybe 70 years from one swing to the next. Another possibility is that the changes are smaller than they appear and that our measurements are still too rough to be sure. The forces behind this dance are simple in principle. The liquid iron ocean above the inner core flows in giant slow currents. Those currents tug on the solid ball through magnetic and fluid forces. The rocky mantle far above also pulls on the core through gravity, because neither the mantle nor the inner core is a perfect sphere. These three players, the solid heart, the liquid ocean, and the rocky shell, exchange tiny amounts of spin between them, like skaters passing momentum back and forth. This is where the elegance shows up. The total spin of the Earth must stay almost constant. If one part speeds up, another part must slow down. So, when the inner core gains a little rotation, the mantle loses a little, and the length of our day changes by a few thousandths of a second. These shifts are far too small for any human to feel, but sensitive clocks and satellites can measure them. The numbers form a quiet conversation between the deep interior and the surface where we live. Some researchers wonder if the inner core's rotation follows a rhythm tied to other slow Earth cycles. The wandering of the magnetic poles, the small changes in the length of the day, the slow drift of certain ocean patterns, all of them shift on timescales of decades. One idea is that they are all connected like gears in a vast hidden clock. Another idea is that they only seem connected, and the patterns we see are partly an illusion of having too few measurements over too short a time. There is also a deeper mystery in the math. The inner core is not perfectly round. It seems to have a soft, lopsided shape, slightly squashed in one direction. That asymmetry means that as it rotates, the gravitational pull of the mantle on it changes. This creates a kind of slow restoring force, almost like a pendulum that wants to settle into a favored position. The pendulum analogy is rough, but it captures the feeling. The core may not be spinning freely. It may be rocking, drifting, and resettling on a time scale longer than any human life. What remains open is whether these patterns are truly cycles or only fragments of cycles we cannot yet see. 60 years of earthquake data may sound like a lot, but it is a blink compared to the age of the Earth. The numbers we have are real, and they are beautiful, and they are not enough. Somewhere beneath your feet tonight, a ball of iron is turning at a rate we still cannot fully describe, following rules we have only begun to write down. When we look at our own world from the inside out, it can begin to feel like the most ordinary thing in the universe. A spinning ball of iron, a churning sea of liquid metal, a thin crust of rock floating above. Yet when we turn our gaze outward to the other planets in our small solar family, we find that almost none of them work quite the way Earth does. And that simple fact opens a quiet, lingering question. How delicate is the arrangement beneath our feet, and how easily could it have turned out differently? Consider Mars, the red world next door. Mars once had a churning core like ours. We can read the evidence in ancient rocks on its surface, rocks that still hold a faint magnetic memory from billions of years ago. But something changed. The smaller body cooled faster. The motion in its metal heart slowed. The magnetic shield faded away. And without that shield, the solar wind began to strip the Martian air, thinning it into the pale, dry sky we see today. One possibility is that size alone sealed Mars's fate. Another idea is that the loss of plate tectonics played a role, trapping heat in the wrong way. The full story remains open. Venus offers a different puzzle. It is nearly Earth's twin in size and weight, which means it should hold roughly the same heat in its interior. Yet Venus has no global magnetic field worth speaking of. Some researchers wonder whether its core may still be entirely liquid, with no solid inner ball to drive the swirling motion needed for a magnetic shield. Others suggest its slow rotation, just one Venusian day stretched across hundreds of Earth days, may starve the dynamo of the spin it needs. The truth lies hidden beneath clouds of acid and a crushing furnace of an atmosphere. We have no clear way yet to listen inside. Mercury, the smallest planet, surprised us by having a magnetic field at all. It is faint, but it is real. For a world so tiny, this seems almost impossible. The leading idea is that Mercury holds an unusually large iron core for its size, perhaps stripped of its outer rock by an ancient collision. Some part of that core must still be molten, still moving, still generating a thin magnetic whisper. But the details are guesswork. Mercury keeps its secrets behind a wall of searing sunlight. Then there is the Moon, our closest companion. Tiny seismometers left behind during the Apollo missions hinted at a small molten layer deep inside. The Moon may have a little iron core of its own, perhaps even partly solid, partly liquid. Long ago, it may have generated its own magnetic field. That field is gone now. The reason it faded and the exact size and state of what remains are still being debated. Set all of these worlds beside Earth, and a quiet pattern begins to form. Our planet sits in a narrow window of conditions, large enough to hold its heat for billions of years, small enough that the heat still flows outward in steady currents, spinning fast enough to twist the liquid iron into orderly motion, cool enough on the surface to keep oceans of water, but warm enough at the center to keep the metal moving. Each of these settings could have been slightly different. A smaller Earth might have already cooled, like Mars. A slower Earth might have stalled, like Venus. A drier Earth might never have built the plate motions that help carry heat from the deep interior up toward space. And above all of this, a thin skin of air. The atmosphere we breathe is only a few tens of miles thick, a soft layer no deeper than the distance to the next town. Below it, the crust. Below that, the mantle. Below that, the great metal sea. And at last, the solid iron heart. Each layer leaning on the next, each one shaped by the layer below. It is tempting to ask whether life elsewhere needs the same recipe: a spinning iron core, a protective magnetic shield, a balanced internal heat engine. Some researchers think these features may be common in rocky worlds. Others suspect that Earth's particular blend is rarer than we hope, a quiet accident of size and timing and chemistry. The question is one of the great open ones in planetary science. So tonight, as the world cools around you, remember the slow, balanced machine humming beneath your feet. A little smaller, a little hotter, a little drier, a little slower, and the story might be very different. We do not yet know how many ways a planet can build a heart like ours. The answer waits, patient and unhurried, in worlds we have only begun to sense. There is something humbling about studying a place no one will ever visit. The deepest hole humans have ever drilled barely scratched the outer skin of the planet. It reached about 12 kilometers down before the heat and pressure forced the work to stop. The center of the Earth lies more than 6,000 kilometers beneath our feet. The gap between what we can touch and what we want to understand is vast, and it may always remain that way. So we study the core the way you might study a sleeping animal in a dark cave. You listen, you wait, you watch for small signs. Every earthquake sends faint waves through the deep interior, and those waves carry whispers about what they passed through. From those whispers, scientists build careful pictures. The pictures are good. They are also incomplete, and there are questions about the core that may never be answered with certainty, no matter how clever our instruments become. One of the largest open questions is the simple matter of composition. Researchers agree the core is mostly iron, with some nickel mixed in. But the numbers do not quite add up. The core seems lighter than pure iron would be at those pressures. Something else is in there. Sulfur, perhaps. Oxygen. Silicon. Hydrogen. Carbon. Each candidate has supporters, and each leaves a slightly different fingerprint in the seismic data. The fingerprints are faint, and the data can be read in more than one way. We may know the recipe one day. For now, we know only that something is missing from our list of ingredients. Then there is the question of how old the inner core really is. Some studies place its birth more than 1 billion years ago. Others suggest it formed much more recently, perhaps only 500 million years back. The difference matters because the freezing of the inner core helps power the magnetic field. If the core is young, then something else must have been driving the field before it appeared. That something is still being puzzled out. Whole chapters of the planet's early life depend on which answer turns out to be correct. The rotation of the inner core is another mystery that refuses to settle. For a while, the story was that the inner core spins a little faster than the rest of the planet. Then newer studies suggested it might be slowing, or even reversing direction over decades. Other work suggests the differences are smaller than once believed. The signal is quiet, the noise is loud, and reasonable scientists looking at the same data sometimes reach different conclusions. The truth is somewhere in the measurements. We just have not yet learned how to read them cleanly. Even the shape of the core hides surprises. The inner core does not seem to be uniform. One hemisphere appears to transmit seismic waves a little differently than the other. Why this lopsidedness exists is unknown. Some researchers think the core may be slowly cooling on one side while crystals migrate across to the other. Some wonder if ancient sinking material from above shaped the asymmetry. The simple image of a perfect iron ball gives way the closer you look to something stranger and more textured. And nested at the very center, that possible inner core remains one of the most intriguing puzzles of all. Its existence is suggested by faint changes in how waves travel through the deepest part of the planet. Its iron crystals may be aligned differently than those around them, hinting at a different history, a different chapter of cooling. Whether it is truly a separate region or just a gradual change with no real boundary is still being argued. The center of the Earth may have a center of its own, or it may not. Pressure, temperature, exact density, the precise speed of slow currents in the liquid layer above. All of these carry uncertainty. We work with ranges, not single numbers. A few hundred degrees, one way or the other, changes the story. A small shift in composition changes the story. The core sits behind a wall of distance and heat that no probe will ever cross. Our knowledge has to come indirectly, gathered patiently, piece by piece. There is a quiet beauty in that limit. Not every mystery in the universe lies in distant galaxies or strange dark matter halos. One of the great unknowns is directly beneath the bed you are lying on. It has been there your entire life. It will be there long after. And while we have learned a remarkable amount about it, we have not learned everything. We may never learn everything. The iron heart of our world keeps a few of its secrets, and tonight, that feels less like a loss and more like a gift. For all the questions we have about the iron heart of our world, our tools to answer them are still very young. We have only been listening to earthquakes with modern instruments for about 100 years. In that small slice of time, we built the picture we have now. A picture with soft edges, missing pieces, and gentle uncertainty. The instruments we use today are far more sensitive than the ones our grandparents had. The ones our grandchildren use will be more sensitive still. One of the most quiet, patient projects on Earth is a global web of listening stations. Sensors buried in remote deserts, on lonely islands, deep in old mine shafts. Each one waits in silence for the next earthquake to send its ripples through the planet. Together, they form a kind of giant ear pressed against the ground. With each new event recorded, the picture of the core grows a little sharper. The shadows shrink a little. The boundaries become a little clearer. Researchers are now placing sensors in places we once thought impossible. On the floor of the deep ocean, where seafloor stations can hear sound waves traveling through the mantle from below. On floating buoys that drift across the open sea. Even on the ice of Antarctica, where the cold and quiet help instruments hear faint signals that would be drowned out elsewhere. Each new sensor adds another angle, another view of the same hidden ball of iron at the center. There are also new ideas about what to listen for. Scientists are studying tiny background hums in the Earth, vibrations so soft they were once thought to be noise. Some of these hums seem to come from ocean waves pushing on the seafloor. Others may come from deeper sources we do not yet understand. If we can learn to read these gentle vibrations, we may not have to wait for earthquakes at all. The Earth may be singing softly to itself all the time in a voice we are only beginning to hear. Computer power is changing the work as well. Each recorded wiggle from a distant earthquake contains a small clue, and there are millions of such wiggles. Modern computers can sift through them in ways that were not possible even 20 years ago. Patterns that hid in the noise begin to step forward. The shape of the inner core's surface, hints of regions that move at different speeds, soft echoes from depths we had not noticed before. The data was always there. We simply could not see it yet. Laboratory tools are growing more powerful too. To understand the core, we need to know how iron behaves at pressures and temperatures we cannot easily reach. New machines squeeze tiny samples of metal between flawless diamonds, while lasers heat them to the temperature of a star's surface. For just a moment, a speck of iron lives in conditions like those at the center of the Earth. Cameras and sensors record what happens. Each experiment teaches us a little more about what the inner core might truly be made of. There are dreamed-of tools too, instruments that do not yet exist. Some researchers wonder if particles called neutrinos, which pass through almost everything, could one day be used to map the inside of the planet. Neutrinos slip through rock and metal as if it were not there, but very rarely they bump into something. A future detector, sensitive enough and large enough, might use them to draw a kind of shadow image of the core. The idea is still mostly a hope. The math is hard and the signal is faint, but the seed of the idea has been planted. 1,000,000 years from now, none of these tools will exist. The sensors will have rusted away. The data centers will be dust. But the question may live on, carried by whoever or whatever is here to ask it. The Earth itself will still have a core, slowly cooling, slowly growing, slowly turning. The continents above will have shifted into shapes we would not recognize. The map of the world will be redrawn many times. Yet that hidden iron ball will remain, doing what it has done for billions of years. 1,000,000,000 years from now, the sun will have grown brighter and warmer. The oceans may have changed. Life may look very different, or it may be gone, or it may have moved on to other worlds. Even then, the core will still be there, quietly turning. Whether anyone remains to listen is a different question. For now, the tools are in our hands, and the mystery is still open. We keep building, we keep listening, and the planet, patient as ever, keeps holding its secret close. Let us step back now, all the way back, and look at the iron heart of our world from the widest view we can imagine. The core does not spin forever. Slowly, across spans of time we can barely picture, it gives up its heat to the rock above. The liquid layer cools, the solid ball grows, and one distant day, far beyond any human lifetime, the motion that powers our magnetic shield will fade. The exact timing is not known. Some estimates suggest billions of years. Others suggest the changes will come in stages, with the field weakening long before the metal ocean fully stills. This slow cooling is not a sad story. It is part of how worlds live and die. Every rocky planet we know carries a hot center inherited from its birth. That heat is leftover energy from the cloud of gas and dust that became the solar system. The same cloud built the sun. The same cloud built the other planets. The iron at the center of the Earth was born in the hearts of stars that lived and died before our sun ever began to shine. Think about that for a quiet moment. The iron in the core, the iron in the liquid ocean around it, the iron in the rocks beneath our cities, the iron in the blood moving through your body right now, all of it was forged inside ancient stars. Some of it was made slowly fused layer by layer in the cores of massive suns. Some of it was scattered outward when those suns ended their lives in great bursts of light. The atoms drifted for ages through the cold dark between stars. They gathered, they cooled, they became part of the cloud that became us. So the heart of our planet is, in a real sense, a piece of stellar memory, a frozen ember from older fires. When you stand on the ground and feel it solid beneath your feet, you're standing on the cooled remains of stars that died long before the first life appeared on Earth. The same is true of the calcium in your bones, the carbon in every cell of your body, the oxygen in the breath you are taking right now. All of it came from somewhere out among the stars. The core's slow cooling connects us to a much larger pattern. Everything in the universe is giving up heat, little by little, to the cold around it. Stars burn through their fuel. Galaxies drift apart. Even black holes, the densest objects we know of, are thought to slowly evaporate over timescales so long they make our planet's life seem like a single heartbeat. The Earth's iron ball is one small participant in this great, gentle cooling of all things. And yet, while it spins, it gives us a gift. The motion of the liquid metal generates the field that wraps our world in invisible protection. That field has likely helped keep the air and water on Earth's surface for billions of years. Without it, the solar wind might have stripped much of our atmosphere away long ago, the way some researchers think it stripped the air from Mars. The mystery of why our core is still warm and active, while smaller worlds have grown cold and quiet, remains one of the open questions of planetary science. It is humbling to think about. A ball of solid iron hidden beneath thousands of miles of rock, doing its slow, patient work, allowing the seas and skies and forests above to exist. We will never see it. We will never touch it. We can only listen for its echoes in the trembling of the ground and wonder. And one day, in a future too far away for any of us to imagine clearly, the iron heart will have given all of its heat to the layers above. The shield will fade. The Earth itself will have long since changed beyond recognition. The sun will have grown and dimmed in its own slow story. The atoms that made our core will, in time, be scattered again, perhaps into a new cloud, perhaps into a new world, perhaps into the body of some being who, like you tonight, will lie quietly and wonder what is below them. That is the way of the universe. Not endings, but transformations. The same atoms, again and again, gathering into stars, into planets, into oceans, into bodies, into thoughts. The iron in the core of the Earth is one small chapter in a story that began before the sun and will continue long after the sun is gone. And tonight, just for a little while, that story includes you. And so we come to the quiet end of our long descent. We have traveled together through more than 2,000 miles of stone and metal, past boundaries no eye will ever see, into a place where pressure crushes atoms into shapes that have no name on the surface. We have sat with questions older than any answer. We have listened to the slow, patient hum of a planet that keeps its deepest secrets close. Think for a moment of where you are. You are resting on the thin crust of a living world. Beneath your bed, beneath the floor, beneath the soil and the rock, there is heat, there is motion. There is an ocean of liquid iron sliding in slow, endless currents around a solid ball of metal the size of the moon. And that ball is turning. Quietly, steadily, perhaps a little faster than the rest of us, perhaps a little slower, depending on the decade. No one knows for certain. It is a strange and lovely thought. Far below the gentle weight of your blanket, a hidden engine is at work. It has been working for billions of years. It will keep working long after this night, long after this week, long after every plan you have ever made. The core does not hurry. It does not worry. It simply turns. And around that turning heart, the planet wraps itself in a soft shield of magnetism. That shield reaches out past the clouds, past the highest mountains, past the satellites and the pale glow of the auroras. It pushes back the wind of the sun. It keeps the air in place. It lets oceans stay oceans and lets life stay life. All of this from a place we have never seen and likely never will. The mysteries we have wondered about together remain open. We still do not know exactly when the inner core began to freeze. We still do not know what light element rides along with the iron. We still do not know why the core seems to have an inner heart of its own, oriented in some other direction, as if remembering an older time. We still cannot say how quickly the core is growing, or how long the magnetic field has left before its next quiet reversal. These questions belong to the future, perhaps to scientists not yet born, perhaps to instruments not yet built. That is a kind of gift in its own way, to live on a world that still has secrets. To know that even here, on the planet we call home, there are rooms we have not yet entered. The deep earth keeps its own counsel. It listens to our small footsteps on its skin and offers now and then a faint signal through a passing quake. We learn a little. We wonder more. Picture the earth from far above, a blue and white marble turning slowly against the black. The night side glows softly with the lights of sleeping cities. The day side shines with cloud and ocean, and inside, invisible from any window, that iron heart turns on, warm and patient. A galaxy wheels around it in slow majesty, billions of stars drifting through their own long evenings. The moon hangs nearby, calm and pale, lifting the tides with a touch no hand could match. You are held by all of this, by gravity, gentle and faithful, by an atmosphere that breathes, by a magnetic field that fans out from the core like the petals of an unseen flower, by a planet that has carried life through every storm, every ice age, every quiet hour like this one. The universe is vast, and yes, much of it is empty and cold. But this small place, this warm room, this soft pillow, sits inside a world that knows how to keep you safe. Let the questions drift now. Let the iron ball turn without you watching it. Let the liquid ocean of metal flow on its slow, unseen tides. The mystery does not need you to solve it tonight. It will be here in the morning, and the morning after that, waiting with the same gentle patience it has shown for 4.5 billion years. We may learn more in our lifetimes. We may not. For tonight, it is enough to rest above the mystery, to know it is there, humming quietly beneath us, holding the world together while we sleep. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.